Hey everyone, and welcome back for another deep dive. Today we're going to be talking about something that you've been asking about a lot lately.
Yeah.
Majorana Fermions.
Oh, yeah. This is going to be fun.
Now, I know that might sound a bit intimidating, when you hear Majorana Fermions, but trust me, this stuff is mind-blowing,
It is.
especially when you start thinking about, you know, what it could mean for the future of quantum computing.
It really is fascinating.
So,
What makes Majorana Fermions so unique is that they are their own antiparticle.
whoa, okay, slow down there.
Okay.
I think most people listening have at least heard of matter and antimatter.
Right.
Like, the idea that if they collide, they annihilate each other
Exactly.
in this burst of energy.
And every particle has an antiparticle.
Oh, yeah.
So, for example, an electron has a positron,
Oh.
the same mass but opposite charge.
Okay.
But Majorana Fermions are theorized to be their own antiparticles.
So it's like this perfectly balanced particle.
You could think of it that way. And this self-conjugate nature is what makes them so interesting for quantum computing.
Oh, okay, I'm starting to see the connection here, but there's a catch, right? I mean, these things were proposed back in like the 1930s.
Yeah, 1937.
If they're so important, why haven't we actually found them yet?
Well, Edgar Majorana first proposed them in 1937, and as fundamental particles, we haven't definitively observed them.
Right?
However, there's another way that they can exist.
Okay.
And that's as quasi-particles in materials called superconductors.
Hold on, superconductors. Those are the materials that can conduct electricity with zero resistance.
Exactly.
But what do they have to do with Majorana Fermions?
So it all comes down to a special kind of symmetry that exists within superconductors called electron-hole symmetry.
Okay.
Imagine you have a perfectly still pond.
Okay.
You drop a pebble in.
Yeah.
You get ripples, right?
Ripples, yeah.
Those ripples are kind of like the excitations in a material. In a superconductor, when you excite the system because of this electron-hole symmetry, you create a quasi-particle that is a mixture of an electron and a hole, which is like the absence of an electron.
So it's like a ripple that's both a wave and the absence of a wave at the same time?
Yeah, it's a bit mind-bending, but the key is that these quasi-particles, which are called Bogoliubov quasi-particles,
Locally above
these
quasi-particles.
can exhibit Majorana Fermion characteristics.
So even though we haven't found Majorana Fermions as fundamental particles, we can create them in a way inside these superconducting materials.
Exactly. And this is where things get really exciting for quantum computing.
Okay.
One of the biggest challenges in building quantum computers is that the qubits, the basic units of information, are incredibly fragile.
Okay.
Any slight disturbance from the environment can cause them to lose their quantum state, which leads to errors.
So it's like trying to build a house of cards on a shaky table.
Exactly.
One little bump and the whole thing falls apart.
But what if we could build a quantum computer where the information isn't stored in a single qubit, but instead is encoded in something much more robust?
Okay.
And that's where Majorana Fermions come in.
All right.
Because they are their own antiparticles, they're inherently more resistant to these environmental disturbances.
So instead of a single vulnerable card, we're talking about weaving those cards together into this strong, stable braid that's much harder to disrupt.
Precisely. And that's the basic idea behind topological quantum computers,
Okay.
which would use the braiding of Majorana Fermions to encode information.
Okay.
It's a whole new approach to quantum computing that could be much more stable and reliable.
That's pretty incredible.
Right.
So where are we now in terms of actually building these topological quantum computers? Have scientists managed to braid these Majorana Fermions yet?
Well, it's definitely not easy.
Great.
There have been a lot of challenges, even some setbacks along the way. For instance, back in 2021, there was a lot of excitement around a claim from Microsoft that they had observed Majorana quasi-particles, but that claim was later retracted.
Oh, wow.
Yeah,
So it's a field with a lot of potential, but also a lot of hurdles to overcome.
absolutely. But there has been some progress, even since that 2021 setback. In 2023, Microsoft came back with a new device,
Wow.
and they believe it shows evidence of topological superconductivity and Majorana zero modes. It's still early days, and there's some skepticism in the scientific community, but it's a potential step in the right direction.
So it sounds like there's a lot of work still to be done, but there's also a sense of optimism that we might be getting closer to realizing the potential of Majorana Fermions for quantum computing.
Definitely. And it's not just Microsoft.
Right.
There are research groups all over the world making progress in this area.
Huh.
For example, back in 2012, a team at Delft University of Technology reported observing possible signatures of Majorana Fermions in nanowires made of indium and timonide This sparked a lot of interest and further research into using nanowires as a platform for studying Majorana physics.
So it sounds like there are a lot of different avenues being explored in this field,
Yeah.
and I've heard about something called poor man's Majorana states.
Yes.
What are those exactly?
That's another intriguing approach.
Okay.
While these states don't offer the same level of topological protection as Majorana zero modes, they provide a simpler experimental platform for studying Majorana physics.
Hmm.
They're like a stepping stone to understanding the more complex system.
So it's like a way for scientists to kind of get a handle on the basic principles of Majorana physics before tackling the more challenging task of creating topologically protected Majorana fermions.
Exactly. In 2023, a study was published showing how these poor man's Majorana states can be created using a theoretical model called a Kitaev chain.
Okay, so we've covered a lot of ground here, but there's one more twist to this story that I want to get to, and it involves something called split electrons.
Yes. The split electron surprise. This was a really interesting discovery published in 2025 in Physical Review Letters. Essentially, scientists found that electrons in nanoscale circuits can behave as if they've been split in two.
Wait a minute, split electrons? How is that even possible?
It comes down to something called quantum interference.
Okay.
Remember those ripples in the pond we were talking about?
Yeah.
Well, in these tiny circuits, you can create interference patterns that effectively make a single electron act like it's been divided.
Okay, that's pretty wild.
Okay.
But how does this relate back to Majorana fermions?
This split electron behavior is thought to be a manifestation of something called the two-channel Kondo effect, which is closely related to the physics of Majorana fermions.
So it's another piece of the puzzle that could help us understand and manipulate these elusive particles.
Precisely. What's really exciting is that this discovery could open up new possibilities for creating and controlling Majorana fermions. Imagine being able to manipulate them simply by controlling quantum interference in nanoelectronic devices.
That could be a game changer for quantum computing. Okay, I'm starting to see how all these different pieces fit together, from the fundamental theory to the experimental challenges and the potential applications. But before we get too far ahead of ourselves, let's take a step back and think about what this all means for you. Like, why should you even care about these Majorana fermions?
Well, imagine a world where we can design new materials with, like, unheard of properties, develop life-saving drugs in a fraction of the time, or even create artificial intelligence that surpasses human capabilities.
Okay, yeah, I mean, those sound pretty awesome.
Right.
But how does any of this relate to these weird particles we're talking about?
Those are just a few examples of what quantum computing could enable. And Majorana fermions, with their stability and potential for encoding information, might be the key to unlocking that future.
So as wild as all of this sounds, it could actually have a real impact on our lives.
Absolutely.
Okay, I'm sold.
Yeah.
But let's be real. This is some seriously complex science. Even with all your great explanations, I'm still trying to wrap my head around it all. Can you help us connect the dots?
Of course. So we started by talking about what Majorana fermions actually are, these mysterious particles that act as their own antiparticles,
Right.
a characteristic that makes them stand out from all other known fermions. The only potential exception might be sterile neutrinos, which could be fundamental Majorana fermions if they exist, but they haven't been definitively observed.
And even if we haven't found them in their fundamental form, we've learned that they can show up as quasi-particles in superconducting materials.
Right. These Majorana quasi-particles are what has scientists so excited about quantum computing.
Because they could be the key to building those super stable topological quantum computers we were talking about, right?
Exactly. By braiding these Majorana fermions together, we could potentially overcome the decoherence problem that's been plaguing other quantum computing approaches.
It's like creating an unbreakable code by weaving these particles together.
That's a great way to think about it.
But we also talked about how there have been some bumps in the road, like that retracted claim from Microsoft in 2021. That must have been a huge setback for the field.
It was definitely a disappointment, but it's important to remember the science is a process of trial and error.
Yeah.
Setbacks are inevitable, but they often lead to new insights and approaches.
So it's like a puzzle where we keep finding new pieces and trying different ways to fit them together.
Exactly. And even though there have been challenges, we're seeing some really exciting progress. Microsoft's new device from 2023, which they claim shows evidence of topological superconductivity, and Majorana zero modes is a potential breakthrough.
But you said there's still some skepticism in the scientific community about these findings.
There is extraordinary claims require extraordinary evidence, as they say. And with something as revolutionary as topological quantum computing, scientists are going to be very cautious.
So what would it take to convince the skeptics? What kind of evidence are they looking for?
Well, one of the key challenges is being able to definitively prove that the signals they're seeing are actually due to Majorana zero modes and not something else. It's a very subtle and complex phenomenon, and there are other possible explanations for the experimental observations.
So it's like a detective story, where scientists are trying to eliminate all the other suspects before they can confidently point to Majorana Fermions as the culprit.
That's a good analogy. They need to gather more evidence, conduct more experiments, and rule out any alternative explanations.
And it sounds like the discovery of these split electrons could be a crucial piece of evidence in this detective story.
It definitely adds a new layer of intrigue. The fact that we can now create these split electron states in nanoscale circuits, which exhibit behavior connected to the physics of Majorana fermions, is a really exciting development. It could open up new avenues for research and potentially provide more conclusive evidence of their existence and behavior.
Okay, so it's like we found a new tool in our detective kit that might help us finally crack the case. But even if we do prove beyond a doubt that Majorana fermions exist and can be controlled, how do we actually go from there to building a working topological quantum computer?
That's the million-dollar question, and it's not going to be easy.
What are some of the biggest obstacles that still need to be overcome?
Well, for one thing, we need to figure out how to scale up these systems. Right now, we're talking about manipulating individual Majorana fermions, or small groups of them. But to build a useful quantum computer, we'll need to be able to control thousands, if not millions of them, all interacting in a precisely controlled way.
So it's like going from building a model airplane to building a real working passenger jet.
Yeah.
The complexity increases exponentially.
Exactly. And there are a lot of engineering challenges that need to be addressed. We need to develop new materials that can host these Majorana fermions in a stable and controllable way. And we need to figure out how to manipulate them with precision at extremely low temperatures.
So it's not just a physics problem, it's also a materials science problem, an engineering problem, and probably a whole bunch of other problems we haven't even thought of yet.
You got it. It's a truly interdisciplinary effort.
Yeah.
And it's going to require a lot of creativity, ingenuity, and collaboration to overcome these challenges.
Well, I have to say, even though it sounds like there's still a long way to go, I'm feeling pretty optimistic about the future of Majorana fermions and quantum computing. It's amazing to think that these tiny elusive particles could have such profound impact on our world. But before we get too carried away with excitement, I think it's time for us to bring it all back down to earth for a minute. What are like the key takeaways from our deep dive today?
Well, I think the most important thing to remember is that even though Majorana fermions might seem like something straight out of science fiction, they're a very real and potentially like revolutionary concept.
Yeah.
Whether as fundamental particles or as quasi-particles in superconducting materials, they have the potential to like completely change the way we think about quantum computing.
And that's because of that unique property we were talking about,
Exactly.
being their own antiparticle.
Yeah.
It makes them incredibly stable, which is exactly what we need to build those more reliable and powerful quantum computers.
Right. And we're seeing progress on multiple fronts, from the quest to definitively observe Majorana fermions as fundamental particles to the development of new devices that might be able to host Majorana zero modes.
We even talked about those poor man's Majorana states, which offer a simpler way to study these particles and understand their behavior.
And then there's that surprising discovery of those split electrons, which could open up even more possibilities for manipulating Majorana fermions.
It's like we're piecing together this massive puzzle.
Yeah.
And with each new discovery, we're getting closer to like unlocking the full potential of these fascinating particles.
It's definitely an exciting time to be following this field.
Absolutely.
And who knows what breakthroughs await us just around the corner.
So true. Well, that's all the time we have for today's deep dive into the world of Majorana fermions. Hopefully you're leaving with a little more knowledge and a lot more wonder about the future of quantum computing. And hey, if you enjoyed this episode, be sure to like and subscribe to the show so you don't miss out on future deep dives into fascinating scientific topics. Until next time, keep those brains buzzing.